Human progress is not a straight line we can always follow back. Some of the most brilliant ideas our species ever produced have vanished for 1,000 years or more. This video explores 20 ancient technologies that were lost for over a millennium, each one a stunning leap in human capability that simply faded from common knowledge. You will leave this journey seeing history not as a simple march forward, but as a fragile tapestry of genius, forgetfulness, and rediscovery. We will uncover how a 2,000-year-old device could predict eclipses and why a sword could bend without breaking. What does it mean when an entire field of science disappears? How many masterpieces of engineering are still hidden, waiting to be found? What forgotten ingenuity from the past most challenges what you thought was possible? In the clear waters off a small Greek island, a group of sponge divers made a startling discovery in 1901. While searching the wreck of an ancient Roman ship, their hands brushed against what seemed to be a lump of corroded rock. It was only later, as the encrusted object dried and cracked open in a museum storeroom, that the true wonder inside was revealed. This was the Antikythera Mechanism, a complex clockwork device from around 100 years before the Common Era, and it would utterly rewrite our understanding of ancient technology. It was not a statue or a simple tool, but a sophisticated bronze machine, an analog computer designed to model the heavens. For decades, this corroded bundle of gears baffled historians. It was not until the mid-20th century that a scholar named Derek J. DeSolla Price dedicated his career to unraveling its secrets. Using early X-ray technology, he peered inside and saw a miniature cosmos captured in metal. The device contained over 30 interlocking bronze gears, some with teeth cut with astonishing precision. These gears worked together to track the complex motions of the sun, the moon, and the 5 planets known to the ancient Greeks. By turning a hand crank on the side, a user could advance the mechanism to any future date and see a prediction of planetary positions, lunar phases, and even solar and lunar eclipses. This was not mere guesswork, it was precise mathematical engineering. The device's creators encoded their deep understanding of celestial cycles into its brass heart. It calculated the 19-year Metonic cycle, which aligns solar years with lunar months, and the longer Saros cycle, used for predicting eclipses. To achieve this, they used a differential gear, a technology once thought to have been invented in the 16th century. The Antikythera Mechanism proves that a group of thinkers in the Hellenistic world had reached a pinnacle of mechanical genius, creating a portable planetarium that could compute the future dance of the stars. Then it vanished. The knowledge required to build such a device, the workshops that crafted its minuscule teeth, the philosophical understanding that saw the universe as a predictable machine, all seem to have faded with the decline of the Greco-Roman world. For over 1,400 years, no device of comparable complexity appears in the historical record. The intricate pathways of this ancient technology were erased, forcing later civilizations to slowly, painstakingly, rediscover principles that had once been known. This single artifact pulled from the seafloor poses a haunting question. If something this advanced could be lost for more than a millennium, what other masterpieces of ancient engineering still lie hidden, waiting to change our story once more? The sea could not save them. For centuries, the navies of the Byzantine Empire held a terrifying advantage over any foe who dared approach their capital, Constantinople, by water. Their weapon was not just fire, but a living, crawling horror that defied the very element it was launched upon. This was Greek fire, a chemical nightmare that clung to wooden hulls and sails, burning with such ferocity that water seemed only to spread the flames. Imagine the sheer psychological dread for an attacking sailor in the 7th or 8th century, watching a jet of liquid fire arc from an enemy ship, knowing that once it touched their vessel, there was no escape. The sea, their only refuge, had become a pathway for the inferno. This was not ordinary fire. Historical accounts, particularly from Arab forces who faced it repeatedly, describe a sticky, adhesive substance that was nearly impossible to extinguish. It could be launched in several devastating ways, most famously through a bronze tube known as a siphon, a pressurized nozzle that allowed Byzantine sailors to project the flaming stream directly onto enemy ships like a primitive, monstrous flamethrower. Other times it was packed into clay pots and hurled as grenades, shattering on impact to unleash its hellish contents. The true power of Greek fire, and the core reason it became a lost technology, lay in its secrecy. Its exact formula was a state secret of the highest order, guarded as closely as any crown jewel. Knowledge of its manufacture was restricted to a very small, likely familial group within the Byzantine court, possibly even the emperor himself. Contemporary sources hint at ingredients like crude petroleum from natural springs, mixed with resins, sulfur, or even quicklime, a compound that reacts violently with water to generate intense heat. This combination may have created the signature effect of ignition upon contact with seawater, making it the ultimate naval weapon. For over 500 years, this technological marvel secured Byzantine naval dominance, famously saving Constantinople from multiple sieges by turning the waters around the city into a fiery moat. Its very existence was a deterrent as powerful as the weapon itself. Then it vanished from history. The pivotal moment seems to have been the brutal sack of Constantinople in the year 1204 during the Fourth Crusade. In the chaos and destruction, the closely held custodians of the formula may have been lost, or the specialized workshops destroyed. The secret died with its last keepers. Today, the exact composition of Greek fire remains one of history's great chemical mysteries. Modern scientists can only speculate based on fragmented medieval recipes and descriptions, attempting to reverse engineer a terror whose blueprint was erased by deliberate secrecy and historical upheaval. Its loss is a stark lesson in the fragility of knowledge. When a technology is so tightly held, so dependent on a single chain of custody, it risks disappearing forever. The siphons fell silent, the recipes turned to dust, and a fearsome chapter in the story of ancient engineering was closed, leaving behind only echoes of its awe and terror in the accounts of those who witnessed its power. A sword that could bend without breaking was more than a weapon, it was a legend made solid. Across the medieval Islamic world and into the tales of the Crusaders, stories spread of blades from Damascus with impossible qualities. They were said to be so sharp they could slice a falling silk scarf in half, so flexible they could be bent into a U shape and spring back true, and so resilient they would not shatter against armor or another sword. This was not fantasy, but the real-world mastery of Damascus steel. The magic began not in Syria, but far to the east, in the furnaces of southern India and Sri Lanka. There, artisans produced peculiar ingots of iron known as wootz steel. These lumpy, mottled cakes of metal were the raw material, traded along ancient routes to workshops in cities like Damascus. It was here that master smiths performed their alchemy. Through a painstaking, closely guarded process of repeated heating, forging, and a very specific controlled cooling, they transformed those ingots into blades of breathtaking performance. The secret was in the structure, invisible to the naked eye. Modern scientists, using electron microscopes, have discovered that authentic Damascus steel contains extraordinary microscopic architectures. Within the metal matrix are carbon nanotubes and incredibly hard nanowires of a compound called cementite. These structures, formed by the precise thermal cycling and the exact trace impurities in the original ore, are what gave the blades their legendary combination of sharpness, flexibility, and toughness. It was a nanotechnology achieved over 800 years ago, Then, the knowledge to create it simply faded away, vanishing between the 17th and 18th centuries. Historians and metallurgists still debate why. Perhaps the specific iron ore mines with their unique cocktail of trace elements like vanadium were exhausted. Or maybe the guilds of master smiths who passed their tacit, hands-on knowledge from father to son were disrupted by war, economic change, or social upheaval. The exact chain of craftsmanship was broken. For over 200 years, the formula was lost. Even today, with all our advanced metallurgy and scanning technology, recreating true Damascus steel with all its legendary properties remains a profound challenge. We can analyze its composition, we can see its nanostructure, but the full, living art of its creation, the feel of the forge and the rhythm of the hammer that the masters knew, that empirical science is gone. The loss of Damascus steel is a powerful reminder that the greatest ancient technologies were not just recipes or blueprints. They were intricate dances between rare natural resources and human skill, a fragile synergy that, once interrupted, can silence a masterpiece for centuries. The Pantheon's dome still defies the sky, a perfect hemisphere of ancient concrete that has endured for nearly 2,000 years. While modern bridges and overpasses sometimes require major repairs within 50 years, this Roman masterpiece has weathered earthquakes, invasions, and the slow decay of time without a single steel reinforcement bar holding it up. Its endurance is not a mystery of luck, but a lost science of deliberate chemistry. Roman engineers did not use the simple Portland cement formula common today. Their concrete was a sophisticated blend of lime, volcanic ash from the region of Pozzuoli, and chunks of rock or brick. For structures meant to endure the sea, like the harbor at Caesarea, they took a seemingly reckless step. They mixed it with seawater. This was not a mistake, it was the secret to its immortality. Modern analysis has revealed that the salt water triggered a long-term chemical reaction within the material. Over centuries, seawater percolating through the concrete dissolves components of the volcanic ash and lime, allowing them to slowly recrystallize into rare, plate-like minerals such as aluminous tobamorite. These minerals fill in any tiny cracks that form, essentially giving the concrete a self-healing property. The material does not just resist decay, it actively grows stronger with age, a stark contrast to modern concrete, which can weaken as water and salt corrode its internal steel reinforcements. This revolutionary recipe vanished with the administrative and economic collapse of the Roman Empire. The vast, organized networks needed to mine and transport specific volcanic ash, and the deep institutional knowledge of the master builders, fragmented and were forgotten. For over 1,400 years, the art of creating such resilient, long-lasting structural concrete was lost to the world, only rediscovered in principle with the advent of modern materials science. Today, researchers are urgently studying these ancient formulas, not for nostalgia, but for our future. In an era of rising sea levels and crumbling infrastructure, the Roman model offers a blueprint for creating seawalls, marine barriers, and coastal constructions that can last for millennia, not just decades. The silent, enduring presence of the Pantheon asks us a profound question. How many other sustainable, resilient solutions from our past are we still overlooking in our rush toward the new? Their ships were not vessels of wood, but cathedrals of living knowledge. For centuries before European explorers dared venture beyond the sight of land, Polynesian navigators were mastering the greatest ocean on Earth. They embarked upon voyages spanning thousands of miles across the open Pacific, discovering and settling remote islands from Hawaii to New Zealand to Rapa Nui, guided by a technology that left no physical trace. This was wayfinding, a complete environmental science held entirely in memory, song, and sensation. Without compass, sextant, or written chart, these navigators relied on a profound, holistic reading of the world. They memorized the precise rising and setting points of hundreds of stars, creating a mental star compass that turned the night sky into a reliable map. By day, they interpreted the subtle patterns of ocean swells, feeling how they refracted around unseen islands far beyond the horizon. They watched the specific flight paths of homing birds at dusk, noted the shapes of clouds that gathered over land, and even sensed changes in the ocean's scent. This was not guesswork, it was a rigorous, teachable system, a complex technology of the mind passed down through generations in chants and stories. The arrival of European ships with their magnetic compasses and chronometers, however, initiated a slow cultural erosion. Colonial authorities often dismissed this ancestral knowledge as primitive superstition, actively suppressing its practice in favor of Western instruments. The intricate star paths and swell patterns, so carefully preserved in oral tradition, began to fade from common memory. By the mid-20th century, this ancient art of non-instrumental navigation was critically endangered, a ghost of a once universal Pacific science. Its near-total loss would have been a profound intellectual tragedy. Then came a man named Maupiailug, a master navigator from the tiny island of Satawal in Micronesia, who held the fading knowledge within him. In 1976, he performed what seemed impossible to the modern world. He captained the traditional voyaging canoe Hokulea from Hawaii to Tahiti, a journey of over 2,500 miles, using only the ancient methods of wayfinding. He succeeded brilliantly, proving to a global audience that this was not myth, but a precise and reproducible science of exploration. His courage sparked a cultural renaissance across Polynesia, a deliberate revival of building canoes, training new navigators, and reclaiming this intangible heritage. The story of Polynesian wayfinding is a powerful testament to a different kind of technology, one built not from gears or concrete, but from generations of accumulated observation, encoded in language and lived experience. Its vulnerability to disappearance reminds us that the most sophisticated systems can be the most fragile, sustained not by blueprints, but by the continuous breath of teaching and practice. Its recovery offers a hopeful counterpoint, a proof that some lost arts, when the last keeper remains, can still guide us home. A library's true treasure was never just its walls or its scrolls, but the conversations that happened between them. The Great Library of Alexandria represented something unprecedented in the ancient world, a deliberate, state-funded mission to gather all human knowledge under one roof. Imagine scholars from Greece, Egypt, Persia, and India walking the same halls, debating, translating, and copying texts on everything from the geometry of the stars to the geography of distant lands. This was not a silent archive, it was a vibrant, humming engine of intellectual synthesis. For centuries, it served as the world's foremost center for research, attracting minds like Archimedes, whose treatises on levers, pulleys, and hydrostatics were housed there, and Heng of Alexandria, who described working models of steam engines and automated temple doors. The loss we mourn is often pictured as a single, catastrophic fire, a dramatic blaze that turned centuries of wisdom to ash in one night. But historians now understand the decline was far more gradual and in many ways more tragic. The library suffered from a slow decay of political support, periods of neglect, and the eventual dispersal of its scholarly community. The texts themselves, painstakingly copied onto fragile papyrus, succumbed to the slow violence of time, climate, and the simple fact that they were not being reproduced. When the institution that valued them faded, the knowledge within them ceased to flow. The works that vanished were not trivial. Entire volumes on advanced mechanics, detailed anatomical studies based on dissection, and precise astronomical charts simply stopped being copied. They became ghosts in the historical record, known only by their titles mentioned in the footnotes of later, surviving books. This created a catastrophic bottleneck in the story of human ideas. Concepts and inventions that had been clearly documented and understood had to be painfully rediscovered more than 1,000 years later. The burning question is not just about one fire, but about the fragility of the chain itself. A library is a living system sustained by the continuous acts of curation, translation, and copying. When that system breaks down, knowledge does not just sit waiting, it evaporates. The legacy of Alexandria is a permanent warning about the cost of taking collective understanding for granted. It teaches us that preservation is an active, endless project. And sometimes what vanishes is not a grand institution, but a single, stunning color, a hue so vibrant its very recipe became a buried secret. The color of their gods was meant to last forever. On the walls of temples like Bonampak in Mexico, a brilliant turquoise blue still shines with an almost supernatural intensity after more than 1,000 years of jungle humidity, tropical storms, and relentless sunlight. This is Maya blue, a pigment of such profound stability that modern chemical solvents often fail to strip it from ancient pottery. Its endurance is no accident of nature, but the result of a sophisticated, sacred technology that fused chemistry with ceremony. To create it, Maya artisans did not simply mix a dye with a binder. They performed a precise alchemy, taking an organic indigo dye derived from local plants and combining it with a specific fibrous clay mineral called palygoscite. The magic happened in the application of heat. Through a controlled thermal process, likely within a ritual context, the indigo molecules were driven deep into the microscopic tubular structure of the clay. There, they formed a stable chemical bond, creating a hybrid organic-inorganic material. The indigo could no longer be washed out or faded by light. It was locked in a mineral cage at the molecular level. This process was almost certainly more than a workshop recipe. It was a technology embedded within spiritual practice. Historical accounts and modern analysis suggest the heating process may have involved the burning of sacred copal incense, intertwining the act of creation with prayer and offering. The knowledge was likely held and protected by priestly classes, a sacred trust as much as a technical skill. Then came the rupture of the Spanish conquest in the 16th century. The deliberate dismantling of traditional Maya societal structures, the suppression of indigenous religious practices, and the catastrophic population decline severed the chain of transmission. The ritual context for creating the pigment vanished, and with it the precise, hands-on knowledge of the process. For centuries, Maya blue was a ghost, a color that could be seen but not recreated. Modern scientists, using X-ray diffraction and spectroscopy, have finally decoded its unique nanostructure. We understand the what and the why of its incredible stability. Yet the exact how of the ancient ritual process, the specific temperatures, the timing, the role of the incense smoke, remains just out of reach. We have the chemical formula, but we lost the ceremony that gave it life. Maya blue stands as a profound lesson that technology is rarely just about materials and steps. It is often a cultural expression, a set of actions imbued with meaning and governed by tradition. When that living context is destroyed, the technology can die with it, leaving behind only its beautiful, silent, and enduring artifacts. This deep connection between measuring the world and understanding our place within it finds a stunning expression in a different kind of ancient tool, one that helped map the very land upon which these blue temples were built. No blueprint or manual accompanied them, only silence. Across what was once the Roman Empire, from Britain to Hungary, small, hollow bronze objects keep turning up in the soil. Each one is a geometric marvel, a dodecahedron with 12 identical pentagonal faces. Every face contains a perfectly circular hole, but the holes are not the same size. They vary from one side to another. The objects themselves are usually just a few inches across, meticulously crafted, often with small knobs at each corner. To date, over 100 of these enigmatic artifacts have been found, all dating from roughly the 2nd to the 4th centuries of the Common Era. And not a single Roman text, letter, or carving ever mentions what they are for. They are a technology without a context, a purpose erased by time. This silence has fueled a century of passionate speculation. Could they have been practical tools? Some suggest they were knitting gauges for creating the fingers of gloves, a theory that fits the varied hole sizes but seems oddly specific for an object found across such a vast empire. Others propose they were surveying instruments, perhaps for calculating distances or laying out military camps on uneven ground. A more celestial theory casts them as agricultural aids, devices to hold up to the sun to determine the optimal date for sowing winter grain based on the angle of light. Yet others see them as objects of ritual or ceremony, perhaps used in religious practices or as symbols of status and knowledge. The very fact that we cannot decide is the heart of the mystery. Their craftsmanship suggests they were valued, but their complete absence from the historical record means the common knowledge of their use, the shared understanding that every Roman soldier or merchant must have had when they saw one, that cultural memory is utterly gone. This loss is profound in its simplicity. We are not missing the formula for a legendary steel or the plans for a complex computer. We are missing the answer to a simple question: what is this thing for? The Roman dodecahedron teaches us that forgotten technologies are not always epic in scale. Sometimes they are the quiet, everyday objects whose meaning evaporates when the society that used them stops speaking. It is a humbling reminder that our own world is filled with items whose purpose might one day baffle future archaeologists. While one mystery hides in plain sight as a beautiful bronze puzzle, another lost technology was designed for a single, devastating purpose, leaving no doubt about the power it once wielded. The story sounds like the ultimate defense, a weapon of pure light. According to accounts written centuries after the fact, during the Roman siege of Syracuse in the 210th year before the Common Era, the legendary inventor Archimedes did not just design catapults and cranes to repel the invaders. He is said to have deployed a battery of polished bronze shields, acting as mirrors, to focus the Mediterranean sun into a single, searing point of heat on the wooden hulls of the Roman fleet, setting them ablaze from a distance. This tale of the Archimedes Heat Ray lives in a fascinating space between myth and plausible science, a ghost of a potential technology that was dismissed as fantasy for nearly 2 millennia. The core idea is not inherently magical. Ancient writers like Lucian and Galen did reference the use of burning mirrors in warfare, and the Hellenistic world possessed a sophisticated understanding of optics and parabolic reflection. The concept was theoretically sound. The true marvel and the reason it qualifies as a lost technology would have been in the execution. To achieve the necessary heat to ignite treated, pitch-covered wood at a meaningful distance would have required an array of large, precisely curved and polished bronze mirrors, all coordinated to track a moving ship and focus their reflections onto a single, shifting spot. This was not a single handheld mirror, but a feat of optical engineering, metallurgy, and real-time communication that seems staggering for its time. For centuries, scholars dismissed the story as an illustrative legend, a metaphor for Archimedes' genius rather than a historical report. The knowledge of how to build such a system, if it ever existed, was completely lost, relegated to the realm of fable. Then the modern era began to test the legend. In the 1970s, a Greek engineer named Ioannis Sakkas conducted a famous experiment. Using 70 polished copper mirrors held by sailors, he focused sunlight onto a wooden replica of a Roman galley about 150 feet away. The ship did indeed catch fire within minutes. Later experiments, including one by the television program Mythbusters, found the challenge more difficult, citing the need for ideal atmospheric conditions, perfectly still targets, and sustained coordination. The results are mixed, but they prove a crucial point: the physics is possible. the line between myth and lost science becomes beautifully blurred. The story of the Heat Ray forces us to ask a profound question about historical memory. How many other legendary devices, from the brazen automatons of ancient temples to fabled unbreakable swords, might be garbled accounts of real, sophisticated technologies whose principles were forgotten? When the context for understanding an invention vanishes, all that remains for later generations is the wondrous effect, which slowly morphs into a tale of magic. Archimedes' supposed weapon was not just about fire, it was an early, haunting glimpse of solar power, a concept that would not be seriously revisited on an industrial scale until the concentrated solar plants of the 20th century. Its legacy is not in the ashes of a Roman ship, but in the realization that our ancestors may have glimpsed possibilities we only later claimed as our own. The open ocean under a dense, featureless sky was a navigator's greatest fear. For the Vikings, whose longships ventured far beyond the sight of land to reach Iceland, Greenland, and even the coast of North America, losing the sun could mean a slow, disoriented end. Yet their sagas hint at a solution, a magical stone that could find the sun on a cloudy day. This was no mythic artifact, but likely a brilliant application of a natural crystal, a technology of light that vanished with their era. The so-called sunstone, possibly a clear piece of calcite known as Iceland spar, cordierite, or tourmaline, functioned on a principle of polarization. Even when the sun is obscured by cloud or fog, its light still penetrates the atmosphere in a scattered, patterned way. By looking through such a crystal and rotating it, a skilled user would see changes in brightness or color patterns. The point where the crystal appeared darkest or clearest would align with the hidden sun's position, revealing its bearing even at dawn, dusk, or when it was just below the horizon. This was applied optics of the highest order, a tool born from meticulous observation of the natural world. Its existence moved from legend toward likelihood with a stunning archaeological find. In a 16th century English shipwreck off the coast of the island of Alderney, a block of calcite crystal was discovered near navigation instruments. This single artifact suggests the knowledge, or the tool itself, persisted in maritime tradition long after the Viking Age ended. Then it faded away. The formal scientific understanding of light polarization would not emerge until the 19th century, meaning this practical technology operated for centuries on empirical genius alone. Its loss, likely as magnetic compasses became more common and transatlantic routes shifted, represents a regression. For a time, sailors may have actually lost a reliable method for celestial navigation under poor conditions, a gap that had to be filled again by later instruments. The Viking Sunstone is a perfect example of a technology that was not invented in a laboratory but discovered in the world. It required no complex machinery, only a deep understanding of a crystal's property and the patience to learn its language. Its disappearance asks us to look more carefully at other ancient tales that speak of magical stones or seeing the unseen. How many were simply descriptions of a forgotten natural science, waiting for us to learn how to read them again? This theme of extracting profound utility from the earth itself finds a parallel in another ancient society, one that mastered a different kind of stone to shape its world in monumental ways. A terracotta jar from 2,000 years ago holds a quiet, shocking possibility. In the basement of a museum in Baghdad sits an unassuming artifact discovered in 1936, a simple clay pot about the size of a man's fist. Inside it, archaeologists found a carefully rolled copper cylinder, sealed at the bottom with asphalt, and within that cylinder, an iron rod. The components were isolated from each other, and the asphalt seal would have held them firmly in place. To the team who unearthed it, the arrangement was puzzling, but to a later researcher named Wilhelm Koenig, a startling hypothesis emerged. This was not a ritual object or a simple container. It looked for all the world like a primitive galvanic cell, a battery. If the jar was filled with an acidic electrolyte, something as common as vinegar or fermented grape juice, a chemical reaction would begin. The acidic liquid would interact with the two different metals, the iron and the copper, creating a flow of electrons, a tiny electric current. Modern replicas have proven it works, generating just over 1 volt of electricity, a gentle but measurable charge. This opens a door to a forgotten chapter. What could such a device have been used for? The most compelling theory points to metallurgy. That small, consistent current would be sufficient for a process called electroplating or electrogilding. A skilled artisan could use it to deposit a thin, even layer of gold onto a silver object, or to give a copper statue a golden sheen. This was not magic but applied electrochemistry. Imagine a workshop in ancient Mesopotamia using jars like these to create dazzling ceremonial objects, their craft powered by a force no one fully understood but had learned to harness. The implications are staggering. If this interpretation is correct, then the basic principle of generating electricity was known, used, and then completely forgotten for nearly 1,800 years, until Alessandro Volta invented his voltaic pile in the year 1800. The loss is total. We have no text, no diagrams, no cultural memory of its purpose. Skeptics offer alternative explanations, suggesting the jar may have been a sacred storage vessel for religious scrolls, the iron rod merely a core around which parchment was wrapped. Yet the specific design, with its asphalt insulator separating two dissimilar metals, feels too deliberate for mere storage. The truth is, we may never know for certain. And that is the jar's most profound lesson. The Baghdad Battery, whether it was one or not, embodies the ultimate mystery of a lost technology. Its function, the very reason for its existence, has been erased. It forces us to accept that an entire field of practical knowledge, one that could alter our view of ancient capabilities, can vanish without a whisper, leaving behind only a silent, enigmatic pot that asks more questions than it will ever answer. The court of Emperor Shun in the year 132 must have watched with a mixture of awe and skepticism. The scholar and inventor Zhang Heng presented not a weapon or a tool for harvest, but a stunning bronze vessel nearly 6 feet tall. Its surface was a masterpiece of art and intention, ringed with 8 dragon heads, each holding a bronze ball in its jaws. Below each dragon sat a corresponding bronze toad with its mouth open, waiting. This was the Hufeng Didongyi, the world's first known seismoscope, and its purpose was to sense the invisible. Zhang Heng claimed his device could detect the direction of an earthquake occurring hundreds of miles away, a feat that seemed like divination. When the earth trembled in some distant province, the mechanism inside would be triggered, causing just one of the 8 dragons to release its ball. The clang of bronze against bronze as the ball landed in the toad's mouth would tell the court which cardinal or intercardinal direction the tremors came from, allowing aid to be sent or warnings issued long before messengers on foot could arrive. The true genius and the profound loss was inside the sealed vessel. Zhang Heng left no detailed blueprint. Historical records suggest the mechanism likely used a clever principle of inertia. Imagine a heavy pendulum suspended freely in the center of the jar. When seismic waves from a distant quake arrived, they would cause the jar to shake, but the pendulum, due to its inertia, would tend to stay relatively still. Its movement relative to the shaking vessel could then actuate a series of levers or channels that would trip the latch on just one dragon's mouth, the one oriented toward the quake's epicenter. It was a mechanical filter, isolating the direction of the primary seismic wave. For centuries in the West, this account was viewed as a curious legend. How could a second-century device possibly achieve such a thing? Then, in the 20th century, scientists and historians began building replicas based on the most plausible interpretations of the ancient texts. Using an internal inverted pendulum or a system of weighted arms, these models worked. They could reliably indicate the direction of simulated tremors, proving Zhang Heng's invention was not myth, but sophisticated applied geophysics. Its loss, however, was nearly total. After his passing, the knowledge to recreate and refine his seismoscope seems to have faded. The device was a marvel of its moment, but it did not spark a continuous tradition of seismic research in China or spread to other cultures. It remained a singular masterpiece, a technological island. The basic principles of directional earthquake detection would not be independently reinvented in Europe until the 1800s, a gap of over 1,700 years. Zhang Heng's seismoscope stands as a powerful symbol of a specific kind of loss, the vanishing of an invention born from individual brilliance. It shows that a single leap of insight, no matter how magnificent, is fragile. Without being integrated into a sustained, collaborative scientific culture where knowledge is systematically shared, challenged, and built upon, it risks becoming a silent artifact, a dragon holding a secret it can no longer tell. The emperor's reaction was not wonder but fear. According to the Roman historians Pliny the Elder and Petronius, a master craftsman once presented Emperor Tiberius with a drinking bowl unlike any other. Fashioned from a special, flexible glass, the vessel did not shatter when deliberately dropped on the stone floor. Instead, it merely dented, and with a few taps from a small hammer, the artisan popped the dent back out, restoring the bowl to its perfect shape. This demonstration of material mastery should have been a moment of triumph, a celebration of human ingenuity. Instead, the story concludes with a chilling turn. Fearing that this unbreakable, malleable glass would utterly devalue the imperial stores of gold and silver, Tiberius ordered the inventor executed and his workshop destroyed to erase the formula from memory. Whether this event literally happened is less important than the profound truth the legend carries. It suggests that the loss of a technology can be a deliberate act, a choice made not by accident, but by those in power to protect an existing economic order. The tale points to a tantalizing possibility in ancient materials science. Could Roman glassmakers, through centuries of empirical experimentation, have stumbled upon a formula that drastically increased the durability of their product? Perhaps they introduced additives like magnesium into their silica mix, or developed a rapid cooling and reheating process akin to modern tempering. They may have created a glass with a different molecular structure, one that allowed for plastic deformation rather than brittle fracture. This was not magic, but a lost branch of practical chemistry. For nearly 2 millennia, the concept of flexible, impact-resistant glass remained a distant dream, a ghost in historical anecdotes. It was only with the rise of modern polymer science that we created plastics to fulfill that role of durable transparency, and only in the last century that we developed tempered and laminated safety glass, or the incredibly resilient Gorilla Glass that now coats our devices. Each is a systematic rediscovery of a property that an ancient artisan might have held in his hands. The story of Tiberius and the flexible glass, whether fact or fable, forces us to confront a different kind of historical loss. Here, a technology did not fade from forgotten scrolls or fall with an empire. It was potentially seen, understood, and then actively suppressed. It reminds us that progress is not an inevitable forward march. It is a path shaped by human choices, where fear of disruption, the protection of wealth, or the simple inertia of tradition can strangle a brilliant idea at its birth. The lost bowl becomes a symbol for all the innovations that never were, silenced not by the passage of time, but by the deliberate hand of the present. The steam hissed from 2 bent tubes, spinning a hollow bronze sphere faster and faster until it became a blur of polished metal. In the 1st century, within the intellectual ferment of Alexandria, the engineer hero demonstrated a principle that would one day power the world. His device, called an eolipile, was elegantly simple. A sealed sphere mounted on a central axle was filled with water and heated from below. As the water boiled, steam escaped through two angled nozzles on opposite sides of the sphere. The reactive force of these jets, like miniature rockets, caused the entire sphere to spin with surprising speed and power. This was not just a clever trick, it was the first documented steam turbine in history, a working model of converting thermal energy into rotary motion. Hero understood the physics perfectly, and he described it in meticulous detail among his many writings on pneumatics and automata. Yet for him and his contemporaries, this was a thauma, a wonder. It was a temple curiosity to amaze worshippers, or a philosophical demonstration for scholars in the library's garden. The conceptual leap from spinning sphere to practical engine was a bridge they never crossed. Imagine for a moment that same reactive force applied to a pump's piston or connected to a millstone's gears. The potential was there, latent in the design. But the social and economic landscape of the ancient Mediterranean offered little incentive to pursue it. Labor, in the form of human and animal muscle, was abundant and cheap within the system of the time. The idea of replacing that labor with a machine powered by fire and water simply did not align with the needs or the imagination of the era. The knowledge was preserved, but its transformative application lay dormant. Hero's manuscripts survived the centuries, copied and recopied, studied by Arab scholars and later Renaissance engineers. They marveled at his ingenuity, yet for over 1,700 years, no one connected the spinning sphere to the backbreaking work of draining mines or weaving cloth. The principle had to be painfully rediscovered and reimagined in a different world, one where labor economics and industrial ambition created a desperate need for mechanical power. The story of the Eelipile is perhaps the most poignant kind of loss. It was not a secret formula burned in a library fire or a craft erased by conquest. It was a road not taken, a future glimpsed but immediately dismissed as mere entertainment. It teaches us that invention alone is never enough. A technology only becomes revolutionary when a society is ready to see not just what it is, but what it could mean. The steam waited silently for a civilization that needed to listen. The grief of the gods could be washed away with a single draft. In Homer's Odyssey, the noble Helen offers a mysterious substance called nepenthe, a potion so powerful it could erase sorrow and pain from the mind, making one forget all hardship. Later writers, from historians to botanists, would treat nepenthe not as mere myth, but as a reference to a real and potent drug from the ancient world, a botanical technology whose recipe has vanished. This points to a profound and often overlooked category of loss, the forgotten pharmacopoeia of antiquity. Beyond legendary potions, ancient healers from Greece to Egypt, India to China, possessed deep empirical knowledge of plant compounds for very specific purposes. They crafted soporific sponges soaked in mixtures of opium, mandrake, hemlock, and wine, which when held over a patient's nose could induce a state of deep unconsciousness for surgeries. They developed complex herbal preparations to alleviate melancholy, calm anxiety, or even induce visionary states for ceremonial purposes. This was not random guesswork, but a refined, observation-based science of biochemistry, passed down through generations of practitioners, often as closely guarded oral traditions. The loss of this bio-knowledge was catastrophic for human well-being. When the societal structures that supported these healers collapsed, or when their practices were suppressed by new religious or medical authorities, the intricate recipes faded. The specific harvesting times, the precise mixtures, the exact dosages that separated a therapeutic agent from a deadly poison, all that hard-won data evaporated. For centuries, the Western medical tradition largely lost safe and reliable methods for surgical anesthesia or the management of severe emotional distress. The wheel had to be reinvented through centuries of trial and often tragic error. It was not until the 1800s that ether and chloroform were rediscovered for surgery, and the 20th century before systematic psychopharmacology re-emerged. Each was a step toward reclaiming a mastery that ancient healers had once possessed. The silence around Nepenthe and its kin is a reminder that technology is not always about metal and mechanics. Sometimes it is the living knowledge of a leaf's property, a root's timing, and a blossom's secret strength. Its disappearance shows that progress in alleviating human suffering is not guaranteed, and that the most intimate forms of ancient technology, those that soothe the mind and body, can be the most fragile of all. Their empire was a marvel of administration without a single written word. Stretching along the Andes for thousands of miles, the Inca governed a territory of immense diversity, coordinating labor, harvests, and tribute across mountain peaks and deep valleys. They achieved this not with paper and ink, but with an elegant, tactile technology of knotted cords called the quipu. At first glance, a quipu appears as a simple bundle of colorful strings hanging from a primary cord. But each element was a deliberate choice, a piece of data in a complex, three-dimensional language. The type of knot, its specific position on the string, the color and material of the cord, even the direction of the twist in the fiber, all held distinct meaning. This was a system of profound sophistication. We know with certainty that quipus served as the empire's accounting ledger. They recorded census numbers, tax obligations, and warehouse inventories with a decimal precision that modern scholars have largely cracked. A figure in the thousands place, the hundreds, the tens, and the units could all be represented by different knot clusters on a single pendant string, creating a portable, durable database. Yet many researchers now believe the quipu's capacity went far beyond mere numbers. The same variations in color, knot, and structure that organized census data could, in a different context, encode narratives, historical records, laws, and even poetry. It was potentially a complete information technology, a woven literature that recorded the stories and laws of a civilization in a form no European eye could recognize. This failure of recognition led to a catastrophic cultural erasure. When Spanish conquistadors arrived in the 16th century, they saw these bundles of knots as primitive talismans or, worse, tools of idolatry. They could not conceive of a legitimate record-keeping system that was not alphabetical. In their campaign to dismantle Inca religion and governance, they systematically destroyed vast archives of quipus and targeted the trained keepers of this knowledge, the quipucamayocs. These master readers, who held the living key to interpreting the full depth of the system, were silenced, their guilds broken. The language of knots was severed from its speakers in a single, brutal generation. Today, scholars can read the numbers on surviving quipus, but the narrative content, the stories and songs they may have held, remains largely mute. We have the grammar of their mathematics, but we lost the vocabulary of their history. The quipu represents a road not taken in the human story of communication, a proof that writing is not the only path to complex data management. Its loss is a stark reminder that when we define intelligence or civilization by our own narrow standards, we risk destroying entire libraries of human thought without ever realizing what was on the shelves. Deep beneath the sun-baked earth of Malta lies a world carved from silence and stone. The Hal-Saflieni hypogeum is not a grand temple on a hill, but an inverted one, a labyrinth of chambers and passageways painstakingly excavated from solid limestone over 5,000 years ago. This was a sacred resting place, a complex where a community honored those who came before through intricate ceremony. Yet walking through its shadowed halls today, one discovers it is not silent at all. It hums with a forgotten science. In certain oval-shaped chambers known as the Oracle Room and the Holy of Holies, the very architecture becomes an instrument. The curved walls, the domed ceilings, the specific proportions of the space, all were engineered to trap and amplify sound in extraordinary ways. A single voice speaking or chanting at a particular pitch does not merely echo, it resonates, filling the chamber with a palpable, vibrating energy that can be felt in the chest. Researchers measuring these spaces have identified a powerful resonance frequency around 110 Hz, the approximate pitch of a low male chant. This is no accident of geology. The builders of the hypogeum appear to have sculpted the rock to target this specific sonic signature. Modern studies in the field called archaeoacoustics suggest that sustained exposure to sound at this frequency can have a measurable effect on human brain activity, potentially quieting the language centers of the brain and encouraging patterns associated with meditation, relaxation, or altered states of awareness. For the people who used this space, this was likely a technology of transcendence. The architecture itself, guided by an empirical understanding of sound waves they could not see, became a tool to shape consciousness, to facilitate a connection between the living community in the chamber and the memory of those they honored. It was a merging of spiritual intention with physical principle, using the environment as a resonant chamber for ritual. Then that culture vanished. The purpose behind this precise sonic engineering, the chants that were used, the specific ceremonies designed to harness these vibrations, all faded with the people who created them. For millennia, the hypogeum sat sealed and forgotten, its acoustic properties lying dormant. The systematic exploration of how architecture can influence mind and body through sound is a very modern pursuit, a rediscovery of a principle that was clearly understood and masterfully applied in the deep past. The silent stones of the hypogeum now speak to us of a different kind of ancient genius, one that did not seek to conquer the world, but to tune the human experience within it, using the very walls of the earth as a medium. Their instruments were not crude, but works of art in steel and bronze. In the ash-preserved ruins of Pompeii and other Roman sites, archaeologists have uncovered medical kits that look startlingly modern. Delicate forceps with fine teeth for extracting arrowheads, scalpels with replaceable steel blades, intricate bone drills, and even speculums for gynecological examinations, all speak of a surgical practice built on precision and anatomical understanding. These were not tools of last resort, but the standard equipment of a Roman medicus, a professional who drew upon centuries of compiled Greek medical knowledge. With these refined instruments, Roman surgeons performed operations that would challenge modern practitioners. They removed cataracts by couching, a delicate procedure to displace the clouded lens. They conducted trepanation, carefully drilling holes in the skull to relieve pressure, and evidence from recovered remains shows many patients survived the operation. They set broken bones with specialized clamps and even attempted plastic surgery for facial injuries. This was possible because their technology was twofold. The physical tools were masterfully crafted from high-quality metals, and they were guided by textual knowledge, the translated works of figures like Galen and Hippocrates, which discussed anatomy, diagnosis, and procedure. Furthermore, they understood the principle of cleanliness, using boiled instruments and antiseptics like vinegar and wine to clean wounds, practices born from observation rather than germ theory, but effective nonetheless. Then, this integrated system of knowledge and tool-making fragmented. With the decline of the Roman Empire and the dispersal of its centralized institutions, the conditions that supported this high level of surgical practice eroded. The economic networks that supplied fine steel and skilled metalworkers broke down. The widespread literacy and access to classical texts diminished. In much of medieval Europe, the refined craft of surgical instrument making regressed dramatically. Tools became cruder, often made by blacksmiths rather than specialized artisans, and the sophisticated techniques documented in ancient texts were forgotten or dismissed. Complex surgeries gave way to more rudimentary and far riskier interventions. This was a loss not merely of objects, but of an entire ecosystem of skilled practice, where the hand of the craftsman and the knowledge of the surgeon were in alignment. For nearly 1,000 years, this refined technological lineage lay dormant. It was only during the Renaissance, with the rediscovery and translation of classical medical texts, that surgeons began to look back and see what had been lost. The designs of the ancient tools studied once more inspired a new generation of instrument makers, helping to rekindle the pursuit of precision in medicine. The gap between those Pompeian toolkits and their 19th century equivalents represents centuries of unnecessary hardship, a stark reminder that technological progress can reverse. It shows that the most advanced tools are useless without the cultivated knowledge to wield them, and that both are vulnerable to the slow forgetting of time. Buried with 2 swords, 2 axes, and bracelets of bronze, the treasure was never meant to be found. In 1999, looters using metal detectors on a forested hill in Germany unearthed a collection of artifacts that seemed typical for the Bronze Age until they brushed the dirt from a peculiar green disk. What they held was the Nebra Sky Disk, a stunning object that would shatter our understanding of prehistoric Europe. Cast from bronze and inlaid with gold, it is not a shield or a piece of ceremonial armor, but a portable map of the heavens, created around 1,600 years before the Common Era. This makes it the oldest known concrete depiction of the cosmos in the world, crafted over 1,000 years before the earliest written star catalogues of Mesopotamia. The disk is a masterpiece of both art and applied science. Against a deep blue-green background of weathered bronze, a golden crescent moon, a full circle sun, and a cluster of 32 stars are arranged. One specific, tightly packed group of 7 stars is almost certainly the Pleiades cluster, a key marker in ancient calendars worldwide. But the true genius lies in 2 golden arcs added later along the disk's edges. One arc, spanning exactly 82 degrees, marks the angle between the sunset positions at the summer and winter solstices, as seen from that hill in central Germany. The disk was not merely a picture, it was a functional instrument. By holding it toward the horizon and aligning the arcs with the sun's seasonal extremes, a knowledgeable user could determine the correct time to add a 13th intercalary month to the lunar calendar, synchronizing it with the solar year. This was vital knowledge, the difference between planting crops at the right time and facing a failed harvest. It represents a profound intellectual leap, the encoding of complex, long-term astronomical observations into a durable, handheld object. This required a society stable enough to observe the sky for generations, skilled enough to work bronze and gold with precision, and organized enough to need and use such a precise calendar for agriculture and ritual. That society was the Unetis culture, a network of early Bronze Age communities across Central Europe. Then they vanished from history, absorbed or displaced by other groups. With them disappeared the specific need for this instrument and the layered knowledge system that created it. The Nebra Sky Disk is a solitary beacon. For over a millennium, no object of its kind appears again in the European archaeological record. Its lonely existence forces a humbling realization: complex abstract modeling of the cosmos, the very foundation of science, was being practiced in the forests of Central Europe far earlier than anyone dreamed. It bridges our journey from physical tools to the most profound loss of all, not just a technology or an artifact, but the very frameworks of thought, the languages and complete worldviews that give such objects their meaning. Their words were not etched in stone, but laid down in ink on fragile pages of paper and parchment, a library built from the desert's edge. In the fabled city of Timbuktu, between the 13th and 17th centuries, a flourishing center of Islamic scholarship produced a legacy of learning that rivaled any in its era. This was not a single great library, but a decentralized treasury of knowledge, with hundreds of thousands of manuscripts held in private family collections, mosque archives, and the personal libraries of scholars. These texts covered every field of human inquiry, from intricate treatises on astronomy and mathematics to detailed legal commentaries, advanced medical manuals with local herbal remedies, and volumes of exquisite poetry and philosophy. They represented the pinnacle of West African intellectual achievement, a sophisticated scientific and literary tradition that developed unique African perspectives, wholly independent from the European narrative of the Renaissance. Within their pages were advanced mathematical concepts for calculating inheritance, precise astronomical charts for navigation across the Sahara, and medical knowledge tailored to the specific diseases and resources of the region. This was a complete, homegrown corpus of science and humanities, a testament to a cosmopolitan, literate society that traded ideas as readily as it traded gold and salt. Yet this knowledge faced a relentless siege, not from a single fire, but from the slow, corrosive forces of time, climate, and political upheaval. The Saharan environment is harsh on organic material. The very paper and ink of these manuscripts, exposed to centuries of extreme dryness followed by humidity, began to crumble and fade. More devastating than the climate, however, were periods of conflict and colonial rule, which disrupted the social and economic structures that supported the scholarly class and endangered the physical safety of the collections. For generations, the guardians of this heritage were the families themselves, who hid the manuscripts in trunks, buried them in desert caves, or walled them into their homes, passing down the duty of preservation at great personal risk. Their heroic efforts saved an astonishing amount, but an untold number of volumes were lost forever to decay, neglect, or destruction. Each lost manuscript represents a vanished chapter, a unique voice, and a line of inquiry into technology, medicine, and the natural world that is now silent. The tragedy is compounded by historical omission, for this vast African contribution to global science was largely excluded from the mainstream narrative of intellectual history for centuries. Today, a monumental international effort is underway to locate, conserve, catalog, and digitize the surviving manuscripts. This work is a desperate race against a second, final loss. Archivists fight the brittleness of every page, scanning them to create a digital shadow that can survive the next millennium. This ongoing struggle brings our journey through 20 ancient technologies to a close, but it makes a crucial point. The process of loss is not confined to the distant past. The millennium-long clock is still ticking for some ancient knowledges, and their survival now depends on our choice to listen, to preserve, and to finally include their wisdom in the story we tell about human ingenuity. A pattern emerges from these 20 silences, a blueprint for forgetting. The loss of ancient technology was rarely a single, dramatic event, but more often the slow unraveling of a complex web. Empires fell, and with them went the vast administrative and economic networks that supplied rare materials, funded workshops, and created demand for specialized goods. When Rome's centralized authority fragmented, the organized transport of specific volcanic ash for concrete ceased, and the master builders who knew its secrets found no new patrons. The intricate recipe for Greek fire died not in a battle, but in the chaotic sack of Constantinople, where the last few keepers of the state's secret may have perished without passing it on. This points to a profound vulnerability in pre-industrial knowledge. Much of it was what we now call tacit knowledge. This is the understanding embedded not in a manual, but in the hands of the artisan, the rhythm of the hammer, the feel of the forge's heat, the intuitive timing of a chemical process. The master smiths of Damascus steel did not work from a written formula. They operated from a deep, embodied craft learned over a lifetime of apprenticeship. When war, social upheaval, or a shift in trade disrupted that chain of master to apprentice, the knowledge evaporated as completely as if it had never existed. Secrecy itself became a tomb. Proprietary methods, whether guarded by a Byzantine emperor or a Maya priestly class, were protected so fiercely that their survival hinged on a perilously thin line of succession. Break that line and the technology became a ghost. Colonial suppression played a devastating role, as seen with the deliberate targeting of Inca quipu readers and the dismissal of Polynesian wayfinding, where an entire system of knowledge was invalidated because it did not match the conqueror's own tools of record. Sometimes the loss was simply economic. A technology became obsolete because the cost of maintaining its ecosystem was too high. Hero's steam turbine remained a curiosity because slave and animal labor was, in that moment, a cheaper and more familiar source of power than building the engines and fuel systems to harness steam. The supporting infrastructure did not yet exist to make it viable. These stories collectively reveal that a technology is not just an object or an idea, it is a living process. It requires raw materials, skilled practitioners, cultural value, and a means of transmission. Remove any one of these supports, and the entire structure can collapse into silence. This realization forces a humbling reflection on our own era. Our digital civilization, for all its apparent permanence, is built on layers of code, hardware, and energy grids that are astonishingly fragile. How much of our own knowledge is tacit, held in the minds of a retiring generation of engineers? How many of our systems are so centralized that a single point of failure could erase critical data? The ancient losses teach us that preservation is not passive. It is a conscious, continuous act of teaching, sharing, and diversifying the ways we hold what we know. They ask us to look at our own world and wonder, what are we, right now, in danger of forgetting? These 20 marvels, from celestial computers to unbreakable glass, paint a portrait of history far richer than a simple march forward. Our journey reveals a complex web of brilliance, circumstance, and profound forgetfulness. Each rediscovery, from the Antikythera Mechanism's gears to the molecular cage of Maya blue, humbles our modern perspective. They force us to acknowledge that our ancestors possessed insights and practical skills we are only now, with our advanced tools, beginning to fully comprehend. The past was not a waiting room for our present, but a landscape of its own sophisticated achievements. These lost technologies fundamentally challenge the comforting myth of linear advancement. Progress, it turns out, is not a guaranteed ascent. It is a fragile path that can double back, fork into silence, or vanish entirely when the delicate conditions that sustain knowledge are broken. What we call a dark age is often not an absence of light, but a forgetting of where the lanterns were hung. The true lesson here is about the nature of knowledge itself. It is not a solid monument, but a precious, flickering flame. It requires more than just a spark of genius. It needs the steady fuel of teaching, the protective vessel of cultural value, and the continuous oxygen of shared practice. From the state secrets that died with their keepers to the oral traditions suppressed by conquest, we see that without this active tending, the flame can go out for 1,000 years. So let this exploration be a call to look differently, both backward and forward. Look at the past with greater curiosity, seeking not just kings and battles, but the quiet work of the artisan, the stargazer, and the healer. And look at our present with a renewed sense of stewardship, actively working to protect the diverse and often fragile knowledge systems that still exist all around our world, from indigenous ecological wisdom to endangered crafts and languages. Their survival enriches our collective future. If this journey through forgotten genius has shifted your view of history, consider subscribing for more deep dives into the mysteries of our shared past. And we would love to hear your thoughts. Which of these lost technologies amazed you the most? Share your choice in the comments